I am Arnab. I'm a postdoc at McGill University. I'll be talking about the progress towards measuring H1 autopower spectrum with CHIME. Hopefully soon I will change the slide, title of my slide and say the fast measurement of H1 power spectrum with CHIME, but today is still progress. One slide on baryon acoustic oscillation. If you have an initial density perturbation at very early universe, when universe is hot and dense, it will equilibrate by emitting a spherical sound wave, and that will be imprinted in the baryon photon fluid, and it will be also frozen in at recombination, leaving an acoustic peak in both CMB and also in the matter power spectrum. And this particular scale is measured in by CMB community very accurately, and the scale is roughly 150 MPC in the Cohen coordinate, and it is with the accuracy of 0.3% by Planck coordinate. It is a little bit old, but that is the accuracy we have. We know the scale very, very precisely. Also, it gives you that this scale is imprinted in CMB, but it also being imprinted in the later stage matter power spectrum. So you have a scale. If you design a survey and if you measure that as a function of redshift, you can understand the acceleration phase of the universe. Also, you know what the dark energy is. And that is the main goal of spectroscopic galaxy survey. This is the result by DESI 2025. I think 3 weeks old data paper it is. So what they are doing is they are basically measuring each galaxy. So each point here is a galaxy. They measure the 3D location of each of these galaxies. They have different tracers, and they just measure the 2-point correlation function, and they also detected this BAO bump in their 2-point correlation function. However, the most highlighted result of their analysis is the dark energy. So this is the dark energy equation of state. So in the lambda CDM framework, you would expect that W naught is constant, is -1, and the time evolution part WA is 0. So in all these plots, so in the lambda CDM framework, you would expect that your lambda CDM point would be here, where W naught equals to -1 and WA equals to 0. However, all the DESI results, when they combine with low redshift survey and high redshift survey, they found that their contours are like in the lower quadrant. It is basically saying that now dark energy is evolving as a function of time, which is really, really interesting, at least to me. Now we should have designed a complementary survey which can probe the same thing and where we can test all the dark energy models. So what we know, so we know CMB, it is a redshift at 1100. We know that this is a thin shell at redshift 1100. We also know from galaxy spectroscopy galaxy survey, where they measured all these individual objects in the sky, and at high redshift they have some JWST observation, but you can clearly see that there are a lot of volume in this observable universe. Is still it's not being probed very precisely, right? So here comes the 20th century intensity mapping, where hydrogen is the most abundant element in our universe. It emits the 21 centimeter line. It is a spectral line. You can do a 3D mapping. You do not need to isolate or resolve individual galaxy. You can make a diffuse map of the sky and then study the power spectrum. If you measure the power spectrum starting from low redshift to high redshift, you can actually measure the dark energy also. And at high redshift, this is the only way to probe the intergalactic medium, which low frequency cosmologists are doing. So rest of my talk, I will just highlight what CHIME is. I will mainly focus on improvement in the data processing pipeline. I also show some of the preliminary result of power spectrum and also the future outlook. So CHIME is a collaboration between many Canadian institutes, mainly like British Columbia and McGill, Toronto, and DRAO, but we also have some partner institute in USA. So CHIME located at DRAO, which is at Penticton in the west coast of Canada. We have 4 cylinders here. Each cylinder contains 256 dual polarization dipole. So in total, we have 1,048 dipoles here. This operates between 400 to 800 megahertz, so redshift 0.8 to 2.5, which is really good for mapping the dark energy or basically the acceleration phase of the universe. It is all the components are fixed in the ground. So we have the north-south axis, true north-south axis along this direction. We have east-west axis along this direction. So it is fixed. It is a distant telescope. Sky rotates, and every day we map the entire northern sky for 24 hours. I showed here some like the local RFI, what we see with CHIME. So we have an LTE band here, we have some TV band here, and some other RFI. But this is not the full scenario. This is only 40% data, and I will show other RFI stuff here in a moment. So this is the radio sky as seen by CHIME. So this is the minimally processed data. We just take the visibility and we just Fourier transforming back to the sky. A lot of things going on here. You see that this is a galactic plane. We see Sige, Cassie at the main lobe, also at the side lobe. Like it is basically leaking the sources by a side lobe as a U-shaped pattern. You also see sun here and also the earliest copy of sun. We do not Nike sample the sky along the north-south direction because the shortest baseline is 30 centimeter. So it is a FFT telescope, right? And you do not Nike sample the sky. So that's why for every bright point source, you see a earliest copy of that bright point source. But there is a region in the sky which is free of aliasing artifact, and we are basically taking that region to do our science. We also do not include the daytime data. So here I am showing some example of individual nights, like 25 nights here. The gray region is basically the daytime data. We throw away the daytime data. We take the entire year of data set, and then we just average all the entire year of data set and make the map without including the daytime data. And that is what is showing here. So this is the map of the sky using all the baselines by after throwing away all the nighttime data. And you can clearly see that galactic plane, but now there is no sun here, right? And we also see all the brightest point sources in the sky. However, we do not include all the baselines in our analysis. We only include the intracylinder baseline. So what I mean by is that we do not include the baselines along the cylinder axis. We only include the baseline which is intercylinder, like between two cylinders. The reason is that those intracylinder baselines will be corrupted by crosstalk and also like large-scale diffuse emission. So when we throw out those baselines, we will get this kind of map where the diffuse emission is basically being resolved out. We will see just the brightest point source in the sky. I also highlighted a box. So this is the region we are currently working on. We do not go to Cassia-Sige region. We also do not go to this region where the galactic plane is. We only use this part of the sky. It is quite huge. And this is called basically North Galactic Cap. The name is given by the EBOS survey. So this is the delay power spectrum. We make a map of the sky. We go to the Fourier domain, and then we take the variance over array. So here it is, I'm plotted here is as a function of declination, as a function of tau. Upper level is basically k parallel. In an ideal scenario, you'd expect that your foregrounds will be here at the 0 delay, but we all see a lot of junks going on here, right? So these vertical lines are basically the foreground leakage from multipath. So we have a standing wave in our along the cylinder, which is imprinted in our beam, and that will give you this multipath propagation, this vertical line. You also see this U-shaped pattern here. And those U-shaped patterns are basically Cassia, Sige, Tau A leaking through far side lobes and create a U-shaped pattern. The color bar here is like data normalized by noise. As you can see that like beyond some delay or beyond some K parallel, you are basically dominated by thermal noise. And this is the region we are working on. So we apply a linear high-pass filter. So we just throw away all these modes. We are only working with this mode. However, a caveat of is that like BO scales are actually here. So we are basically losing the BO scale in this first analysis. So we are trying to measure the power spectrum here, but I think in future we will go and try to work on this region. So after foreground filter, this is the foreground filter map. This is still you see a lot of stuff here, right? So this is basically the very bright point sources leaking through side lobe. This is Cassia. No, sorry, this is Sige. There is Tau A. There is Fargo A, and also we see foreground leakage from the sources in the main lobe. So these are the main lobe foreground leakage. And also there are a lot of artifacts which are probably coming from RFI. However, we take that data, we apply a threshold pixel masking, basically saying that if any pixel is above 6 sigma or 3 sigma, you just flag it. So we use that flagging, and then we, in our first analysis, we do a cross correlation. So this is led by Seth Siegel and Richard Shaw, and we published this back in 2022. So what we did is we know from EBOS catalog where the galaxies are, and we just take that location in the sky or location in the map. We just take a 1D spectrum along the line of sight, and then we just stack it, and we get a booming detection in all these three tracers. So ELG is emission line galaxy, LRG is luminous red galaxy, and quasar. And quasar, we get the highest detection, which is like 11.1 sigma, and that is back in 2022. So this is where we were in 2022 and what we are doing so far. So as I mentioned, this is the data from 2022. This is data cube from, and this is the same data cube we used for for the cross correlation. And this also shows the power of cross correlation. If you have a lot of artifacts, you can still cross correlate, you can get a detection. But this data cannot be used for autocorrelation, right? Anyone can understand. If I take this data and measure a power spectrum, that will give huge bias. So this is what I have been leading for last 3 years, along with Liam Gray, which is the software developer at UBC, and Seth Siegel at Perimeter, who is a research scientist. So you see that this is the work, for 2.5 hours of work resulted into this clean map. And this is the map we are using for the auto power spectrum. And this is the cleanest map we have seen with CHIME after telescope turned on. We have not seen this. This is the this clean map before. So the question is how we go from left to right. This is not a magic, and we worked really, really hard to get off all this effect and go to here. And this is the same channel, same set of data set, just an improved analysis pipeline. So I'll now focus on how we go from left to right. So the first thing we worked on, like how improving RFI flagging, bad data identification, and removal of systematic. So we have, I don't know, tens of RFI flagging algorithm we developed within our collaboration. So I'll highlight some of those. One is Stokes-Tsai masking. So we make a Stokes-Tsai data, then apply the high-pass filter in time, remove the background sky. That will remove the background sky, but all the narrow transient RFI will be present in this high-pass filter data. We then beamformed along the declination axis and then find the outlier there. And also we do the same thing with the low-pass filter. So this is the one single channel looks like. So x-axis is basically RA, y-axis is basically declination. You see that a lot of things going on. Left-hand panel is before flagging, right-hand panel is after flagging. If I zoom into this region, you can clearly see this very narrow transient RFI leaking at different declinations. So it could be like a RFI scattered from a plane which is just flying above CHIME. But using this technique, we clearly isolate those things and we actually flag that thing, right? So this is the power of this one masking algorithm. Second is we also take a radiometer test. So we have a variance of the data based on our weight data set. So we take a 30 millisecond even and odd difference. And in that difference, you would expect that the residual would be just noise, right? The sky will drop out, residual should be noise. And we then normalize by this the expected radiometer equation. And this is the quantity being plotted here. So you see that we obviously we do not see noise, but we see lot of RFI, lot of transient RFI, lot of narrowband RFI. This is the LTE band. But more interestingly, we found that there is this blob kind of feature. This is basically a Russian satellite hovering over Canada. So I don't know what they are doing, but they are basically emitting in our band. And if you just compress this color bar, you also see some sporadic emission coming from the same satellite along this region also. However, based on this metric, we identify all of this and then we flag it. So we get rid of most of this RFI here in the left panel and we go to here. This is our second algorithm. The third most important algorithm is chi-square test. So we apply a very high-pass linear filter of basically getting rid of foreground. You expect that if you remove the foreground, the data should be noise, and then you generate a chi-square value from that, and that is being plotted here. So in ideal scenario, chi-square would be like close to 1, so color bar is 0.9 to 1.2. We can clearly see that within this chi-square test, we see still some RFI leaking here, so like very narrow band RFI, very transient RFI, all this stuff. This is the daytime, so we are not taking those things. And based on this plot, we can find those outliers and flag it, and we'll go back to this thing. This is a more clear RFI flagging algorithm. However, what happened is that we started from 40% data. Now we are 72% data flagged for this particular night. For some nights, we are flagging 80%. So this is a huge flagging. With this huge flagging, there are more issues which we understand. So first, I would mention that we have a many different validation technique to find out bad nights throwing away. So this is the delay power spectrum. X-axis baseline, y-axis delay. In ideal scenario, all your foregrounds would be here at within the wedge, and high delay modes would be free of foregrounds. But if you have a narrowband gain error or any RFI, that will leak power to high delay. So in every day, we see this plot and we find out which is the good night, which is the bad night. We also have 5 or 6 more validation plots. I am not going into that. But after throwing away all those nights, we ended up with 94 good nights from 2019. This is quite a lot of bad nights finding and throwing away. So, okay, so with this excess flagging, then there are very subtle issues in the data averaging. What happens is that if you have a day-to-day instrumental stability, so this is a toy example. If you have a gain variation as a function of day, so what will happen, for one day, you will get something like this, and on the second day, day 2, you will get something like this as a function of frequency. Now, your RFI mask is also complicated. When you take the average of that, you will get this black line. So this black line is basically saying that you basically imprinting this sharp feature in your data when you just take a simple average. If you now do the Fourier transform, anyone can understand this sharp feature will leak power to high delay. So one of the things which we understand is that CHIME is basically made of steel and aluminum. So one of the day-to-day instrument instability is basically focal line expansion and contraction. So since the temperature varies, this focal line will basically expand and contract, and that is also like close to 10% effect, and we cannot ignore that effect in our analysis. So currently we are working on how to model this and remove this from the data, but this is one example of day-to-day instrument instability can leak power to high delay. Another one is basically gridding. For each frequency sample, we basically go from 10 seconds to 20 seconds, and Earth is also rotating, right? So for each frequency, when you take an weighted average and put it at the array bin, what happens is that this complicated mask will put the center of the array bin at the different location, right? And this is also function of frequency. This is one frequency, then you go to another frequency, then you go to another frequency. You are basically imprinting another systematics, which is like frequency dependent systematic in your data while you do this gridding and averaging. This is also leaking power to high delay. So what is the solution? So what we did is we take the time stream data, we beamform along the north-south direction, and then we use a constant delay cutoff to filter the foreground, and then we do all the average. So this is a single example of that. So this is different east-west baseline. We do not take the intracylinder baseline in our analysis, but I'm just showing here for completeness. Y-axis is basically your sign of zenith angle or the declination axis. In this beamform data, you just take a constant cutoff, which is roughly 200 nanoseconds. We filter out the foreground, and then we do the average. So we first removing bulk of foreground, and then we take the average. And this is what gives us a very good result. So first, I'm showing the bad one. So you first beamform to Virgo A. So top panel is 0 cylinder separation. This is the 3 cylinder separation. You see that there's a before foreground filtering. But if you take this data, apply foreground filter and grid it, you still see that there is a residual which is roughly at the order of 1 Jansky. This will not allow us to detect H1, right? So instead of what we did, we take the time stream data, we filter the foreground, and then we take the average, and this gives us nothing. Like you do not see anything here, just noise. So this is the improvement we made by filtering the time stream and then doing all the average, like gridding and day average. Lastly, this is the last RFI flagging algorithm which we have. So we still see that after all these things, there are some still RFI leaking through our data, which is kind of frustrating, but this is what it is. And then we use the sum threshold method to find out all these junks and throw away 5% of data on a daily level. And this is our final data for a single night. Then we average all these nights, and these are the nights available from 2019. You see that we processed all the nights present in the 2019, but there are quite a sparse coverage as a function of frequency. Currently, we are working on this band 2, which is roughly 600 to 700 megahertz. We also have good data in band C. We will work on band C later on. So this is like Redshift 2, close to Redshift 2. So we rewrote the entire pipeline. This is not only, again, not only me and other 2 people, we rewrote the entire pipeline, and we have a dedicated pipeline for the measurement of the auto power spectrum. And this is the result we get after all these changes going from left to right. Okay. So also you see that still there are some very bright point sources like cache, CK leaking to silos. So what we did is we apply a linear mask here. We know where the sources are. We know what are the flux values of that. We just generate a mask. We then apply that to the data, compare with the noise, and we use this data for our science analysis. Okay, so for the residual error quantification, we again beamform to CK. You see there is a 3000 Jansky source in our band, is a frequency as a function of our angle. After foreground filtering, we go to the residual, which is roughly of the order of 0.1%. It is really great. We can do this for many bright point sources, like this is all the different lights corresponding to different brightest point sources in the sky, above 10 Jansky. I am plotting here, I also normalized by the expected flux. So y-axis is basically fractional error. You see that the fractional error is roughly 0.025%. Like it is fluctuating between that. RMS is less than 0.01%. This is a great improvement, and this is what we need for H1 direction. So first, what we checked after all these things, we again run the stacking pipeline so that we make sure that we are not killing the signal, right? So again, we get a detection. This is a small subband, 1100 megahertz subband. We stacked on Quasar catalog from eBOS. We still did get a detection. So it is giving us the confidence that we are not killing the signal. This is the 2D power spectrum. Left-hand panel is data, right-hand panel is data normalized by noise. In a perfect scenario, what would expect that your pixel value should fluctuate between plus minus 3 sigma, and that is what you are getting. And in the data, you are just seeing the fluctuation between positive and negative. So it is basically dominated by noise. Next is the histogram plot. This is all the data points falling in each 1D K-bin. I plotted data and also noise. There is no outlier. All the data points looks consistent with noise. So this is the 1D power spectrum. This is very preliminary. I throw away the y-axis level here. This is still under review within the collaboration. This is the zero line. If you see just noise, it would be fluctuating between around the zero line. You get a positive signal here. Currently, we are working on fitting the model to this data point. However, what we can do, we can confirm that this is not foreground residual or narrowband systematics or anything, because those will also give a positive signal, right? So there are many things which can go wrong. We can have a narrowband RFI, we can have a narrowband gain error, which will couple with foreground leak power to high delay, which will basically looks like you are detecting H1, but you are not. So we designed many jackknives. So these are all the statistical tests, not all. We have 4 or 5 more. I just highlighted only 4 here. What is basically doing is that we design a jackknife. If we fail, that would be cross mark. If we do not fail, that would be green mark. So far, we only get the green mark. That is good. That is basically giving us confidence to move forward. But I will only highlight the first 2, not anymore. One thing one can argue is that, okay, this is the mask you are applying, right? This is the main lobe mask, this is the side lobe mask. One can clearly say that, okay, you are masking those bright point sources, but what you are seeing is the faint source side lobes, right? That can also happen. So we design a jackknife, which is we go to 20 Jansky side lobe cutoff, you are only left with 43% sky area. In other extreme, you go to 60 Jansky cutoff, you go to 76% sky area. This is the only very few brightest points like ISSI, all those sources. What will happen is that if you see the power spectrum, which is coming from side lobes, that will basically reduce your power as a function of flux cutoff. So here, main lobe cutoff is fixed. I just changed the side lobe cutoff 20 to 60 Jansky. And with this change, you see that the power is not moving, right? It is all our data points are within 1 sigma. So it is basically saying that you do not see the side lobe residual. Another one can argue that if you have a gain error or if you have a narrowband systematic, that will be multiplicative and that will leak power to the high delay. So we have this 5 Jansky main lobe cutoff. We keep it the side lobe cutoff fixed to the 60 Jansky. In one extreme, we apply many bright point source flux cutoff, go to 66.2% sky area. In another extreme, we just have 1 pixel here. So again, the argument is if you see foreground, for different cutoff, your power should vary. But this is what we do not get, so which is again really good. We don't see any changes in the power. It is just lying at the same region and just on top of each other. Okay, so these are the 2 jackknives. Yeah, so these are the 2 jackknives we performed. We have many more jackknives. I'm not going into all those details, but both of these jackknives are passing. So okay, so lastly, I will mention what is the future direction towards getting the BO scale back. So what we did is we applied this linear high-pass filter. We also do not include the intracylinder baseline. So we are only using this region in this 2D space. Your BO scales are here, so you are basically filtered away this BO wiggle, and we are currently working on just measuring this tail part of your power spectrum. However, we are still hopeful, we are optimistic, we are not pessimistic that we will get back this BO scale in near future. It will take more time, let's say 5 years or 10 years, but we are hopeful that we can do our science in this BO scale. So this is my summary slide. So CHIME is mapping the large-scale structure from redshift 0.8 to 2.5. We have identified bulk of systematics, remove it from the data. We made in progress in the auto power spectrum. First result is coming soon. Stay tuned. Probably in the summer, we will submit this result to the journal. And we made many statistical tests to rule out the systematic contamination. Currently, work is going on template feeding to the data. I'll stop here. Thank you.
Do we have time for a few questions? Laurent?
Exciting result. So this is very aggressive RFI flagging. How much data is left after all these steps?
I think we are flagging close to 70 to 80% on a daily basis. So it's quite a lot. So the scenario at DRAO is not good. We initially thought that it is actually a radio quiet zone, but we find that when aeroplane is moving over CHIME or something, like it is basically broadcasting to the CHIME beam, and we are detecting all those RFI. Also note that the CHIME beam is really large, like it is horizon to horizon. So we are heavily sensitive to RFI. And that is the main drawback in our analysis previously. but we managed to clean those up, mostly.
Questions in the back?
Just from my curiosity, because I'm not from cosmology background, most of the images that I've seen today are dirty images. Dirty images means it's uncleaned. There's an algorithm in radio interferometry when you suppress the side lobes and feed the main lobe, right? So basically, when you applied those masks, you basically remove those side lobes, right?
Yeah.
So do you think implementing a clean-based algorithm might help in this aspect because you will be saved?
I think we try to make our entire pipeline linear. Clean is non-linear. Clean does not have any mathematical, or I would say very strong mathematical description. We are working on developing a beam model which has the side lobe, and then there is a M-mode deconvolution technique. I'll not go into the details of that. So if you have a beam model, you can actually forward model how the source looks like, and then you just try to deconvolve in the M-mode space. So this is not clean. This is our own technique in the M-mode pipeline, which we can do. We are currently working on that, but so far, we are just applying a mask.
Okay, thanks.
Thank you for a very nice talk. Is it possible to constrain primordial power spectrum with the results?
Not in 10 years, I think, next 10 years. Yeah, I think we need to get back those linear modes, right? To do all this science, which we actually promised to do. CHIME is designed to do that. But I think the main challenge is this cross-coupling within the cylinders, and which is basically imprinted on our beam. So all the linear scales are gone. We are only measuring highly nonlinear scale, where modeling is also a challenge on those highly nonlinear scale. But if we go back those scale, which will be probably next 10 years, then we can do all these sciences we have promised.
Okay, thank you.
If I may just quickly follow up on that, I mean, you can, model those. They're not highly nonlinear. I would call them quasi-nonlinear scales. And you can sort of, forward model them as well.
Yeah, we are actually doing that. That is what we did in the cross correlation. We found that it is not so easy, as you understand. It's still difficult, right? The nonlinear scale is. There are finger of God effect, RSD, and all those terms, and modeling those. There are dedicated work going on in the modeling.
There's a huge community doing large scale structure in a fully Bayesian forward modeling approach that includes the most highly nonlinear scale.
That is exactly what we are doing. That's why I have not shown the MCMC feed. We are working on it, but yeah.
Maybe one final question while the next speaker comes down.
Yeah, so it was very interesting. You ruled out some systematics. So you're seeing dominant systematics, or are you suggesting that you action?
I would say stay tuned. I will not reveal that. It is under collaboration review. So far, all the jackknife we did, I think 8 or 9. Almost all jackknife we passed. But we do not have the chi-square value or the chi-square test, just because we do not have the noise covariance matrix. We finally managed to generate all the noise covariance matrix, and by looking into those plots, we are passing those jackknives, but you need to have a statistical value or quantity of that, right? So I hope within 2 or 3 months, the paper will be in archive.
Okay, look forward to it. Thanks.
Let's thank the speaker again.